Okay, we're going to continue on here, chapter 16. We're talking about thermodynamics. So remember, the idea of sort of thermodynamics is the idea of whether or not a reaction will basically take place. So as we talked about last time, we talked about the idea of spontaneity. And when we talk about sort of a reaction being spontaneous, sort of in this context, as we talked about last time, again, it has really nothing to do with how fast or slow a reaction takes place. Again, a lot of people, as we mentioned last time, when they think about spontaneous, they think it occurs really, really fast. And the sort of use of spontaneous in thermodynamics is the use of whether or not this reaction will take place under these conditions without any type of input or anything done to it to help it along, and it will just sort of naturally occur. And that's what we mean when we say something is spontaneous. It means, again, that under those conditions, it could be really fast, it could be really slow, it could be somewhere in between, but this reaction should take place the way it is written. If something is non-spontaneous, obviously means the opposite there. Under these conditions, with no intervention, this reaction definitely will not take place. Sort of what we think about that happening means that if a reaction is spontaneous, typically the way it is written, we would be going from reactants to products, and products would be favored thermodynamically in this reaction. If it is a non-spontaneous reaction, it means that basically reactants would be more favored. The reaction would not proceed as it's written. It would kind of hang out there on the left-hand side. One of the couple of ways that we can sort of look at whether or not something is spontaneous or not is we could use entropy. And entropy is delta S, or the change in entropy. And the entropy of the universe is one thing that we could look at. And the entropy of the universe is really made up of two things: the entropy of your system plus the entropy of your surroundings. And remember that entropy is basically the amount of disorder, craziness that occurs. So the more disorder that you have, the more entropy you have. And actually, for entropy values, as we saw, it actually would become more positive. So if the entropy is increasing, it'll become more positive. To calculate the delta S of the system, which is usually your reaction as well, you basically just kind of take the delta S of your products minus the S of your reactants, again, taking basically the coefficients into account. You would look up the values for all your product side, you look up the values for all your reactant side, and basically kind of sum those guys together in this case and subtract them. If you do end up again with a positive value for the system, it again means that the reaction may or may not be spontaneous, but what it really will tell you is, did the amount of disorder increase or decrease as a result of this reaction? One way you can predict whether or not the order or disorder will increase, or the disorder will increase, is you could look at a reaction if there's gas molecules involved. If your reaction produces more gas molecules than it started with, then the amount of disorder will increase and it'll become more positive. If you actually end up with less, for example, gas molecules, then the delta S of the system would be more negative. We could calculate the delta S of the surroundings by taking minus delta H of the reaction, which is our enthalpy, divided by the temperature in Kelvin. And the delta S of the surroundings is related to whether or not the reaction is exothermic or endothermic. If it's an exothermic reaction, it's going to give off that energy to the surroundings. What that's going to do to the surroundings actually, in a lot of cases, increase the disorder of the surroundings because it gained more energy. And we would see for the surroundings, it becomes positive. And that's why really the negative is here, because if it's an exothermic reaction, delta H would be positive. Negative and negative will turn our delta S of our surroundings into a positive number. Opposite is true if the reaction is endothermic. It's going to suck all that energy out of the surroundings, and that's going to cause the surroundings to have more order. And if we had an endothermic reaction, our delta H would be positive. Positive and then negative will give you a negative value for the surroundings, and that means that the disorder is decreasing in the surroundings or the order is increasing. you add both of those things together and you calculate the delta S in the universe and you hit a positive value, that means the reaction is spontaneous by looking at the delta S of the universe. Now, we saw at the end last time that we may not want to always sort of think about both the system and the surroundings. And a lot of times we're interested in sort of what we're doing or the reaction or the system. So we could use another value, which is Gibbs free energy, delta G. And delta G is also calculated by taking the delta G of formation of your products minus the delta G there of your reactants in this case. And this would be a situation where you would look up in a table, again, much like you do for delta S and delta H, and take the coefficients into account and calculate them. Remember that the delta G for things that in their natural state, like H2, N2 uncombined, will have delta G values of zeros, much like you see with delta H values. Only entropy values will actually be there for things in their natural state. We also saw another equation that the delta G is equal to delta H minus T delta S. And this would be an equation that you could use, for example, if you have the delta H and delta S given to you, or you calculate, I suppose. And this is enthalpy and entropy working together here, along with our temperature here in Kelvin. Now, you can actually use delta G to determine spontaneity of a reaction. If delta G is negative, then it's going to be a spontaneous reaction. If delta G is positive, it will be a non-spontaneous reaction, the way it's written. A couple of things you do have to look out at is units. And again, in terms of units, just a rundown of the common units for all these thermodynamic sort of values. Delta H, which is our enthalpy, is typically in kilojoules. Delta S is typically in joules. And delta G there is typically in kilojoules. So you do have that unit issue right here, definitely in this formula. And it's a very common mistake that people make a lot, which is they don't convert the units. So you have 1 in kilojoules, which is delta H, and you have 1 in joules, which is delta S. So you do need to do that conversion. It really doesn't matter which way you do it, but you do need to make sure that they're in the same units. Otherwise, you're going to be in trouble. Any questions on any of that stuff we talked about last time there? All right. Now, a lot of times in this chapter in thermodynamics, they will sometimes not really give you numbers or anything like that, but they will give you some conditions, and sometimes they'll ask you sort of, based on these conditions, do you expect this reaction to be spontaneous or not? And we could do that with this equation. So I'm actually going to write the equation a couple more times here, and we'll look at the different sort of scenarios that occur. And over here for this side, delta G, delta H minus T delta S, and I'll put one over here, delta G equals delta H minus T delta S. All right, so let's look at the different sort of scenarios that could occur in this equation. So let's say we have sort of the first box here, and in the first box, our delta H is endothermic, and that means that our delta H here is positive. And over here to the left here, we are increasing our entropy, which means our delta S is also positive as well. We do need to remember that the delta H is in kilojoules, the S is in joules. So it's got like a 1,000-fold jump on the delta S to begin with. So in this particular case, the only way that this reaction would be spontaneous and lead to a negative delta G would be you would have to get this part of this formula a lot larger than the front part. And the only way to do that in this case is through temperature. And this would occur only at really high temperatures. So at really high temperatures, what you're going to be able to do is get the back part of that formula to be a larger number than the front part. And then you basically be taking a positive number minus a larger negative number there, basically. And you will then end up with a negative value for delta G. So the delta G will be negative at high temperatures. It will be positive at low temperatures, which means if you have a positive delta H and a negative, I'm sorry, a positive delta H and a positive delta S, the reaction will be non-spontaneous at low temperatures because the back part of that cannot get large enough to overtake the top part or the front part. If we look at the next scenario here, which is in this box, our delta H is negative, so that's negative, and our delta S is positive. In this case, no matter what the situation is, because temperature is always going to be positive in this case because it's Kelvin, you're always going to hit a negative number at all temperatures. So this reaction would be spontaneous at all temperatures, and really there's no way to not to get it spontaneous because of the signs of delta H and delta S. If we take a look at the third box over here, in this case, we have an endothermic delta H, which is positive. We have a decrease in the entropy, which is negative. So much like the top right there, because this guy is going to be negative, it's going to turn this back value into a positive number, no matter what you do, which means it's going to be a positive number at all temperatures. So it's going to be non-spontaneous at all temperatures. Again, because of that negative delta S or entropy in this case. The last sort of situation is over here in this box. And in this box, we have a delta H that's exothermic, which is negative. And over here, we have a delta S that's negative. So in this case, that negative, again, on the back part of this is going to turn this into a positive number, which means as long as that positive number is less than the negative number, and that will occur at low temperatures. So at low temperatures, this guy should be spontaneous. If you hit high temperatures, then the back part of that formula will then be larger than the front part, and you'll actually end up with a positive value of delta G. So you could actually use this equation, and if you know really the sign of sort of delta H and delta S, you could use that to determine whether or not a reaction would be spontaneous at particular temperatures, or really sort of what temperature it is. In certain cases, this reaction can be either enthalpy driven or entropy driven, depending on sort of the situation that's occurring, and depending on really which part of this equation is larger. So, you know, if you have this equation and this part is larger than this part, then it would be more entropy driven. And obviously the opposite would be true. If the delta H is larger, then it would be more enthalpy driven, this reaction, the energy part versus the sort of disorder part. Any questions on that there? So why don't we try one here? Let's say at 25 degrees Celsius, is this reaction spontaneous? So take a few moments there and calculate the delta G, see what you get. Okay, so let's take a look and see. So obviously we have H and S. As we talked about last time, there are a few different equations that involve delta G. So in this case, since we do have delta H and delta G, we might as well use the equation that has both of those in it. In this case, we do need to convert our temperature there to Kelvin, so 298. And putting it in here, we will end up with our delta H. It's 177.8. I am going to multiply it by 1,000. And the reason, again, I'm doing that is to get my units the same. So that's going to put it into joules for me. If you want to leave it in kilojoules, that's fine, but you do need to convert that guy into kilojoules. So again, it's your choice, whichever way you want to go. We're going to go minus our T, which is our 298, and our S, we'll go right about there on our graph there, 160.5 joules, basically. And we will end up with 177.8 times 1,000 to convert to joules, minus 298 times 160.5, which is already in joules. That's going to give us a 129971 joules. are approximately 130 kilojoules in this particular case. First off, any questions on that calculation? That means that at 25 degrees Celsius, this reaction is non-spontaneous. And that is because we ended up here with a positive value for our delta G. So this reaction would be non-spontaneous. Now, can we figure out, for example, when this reaction would become spontaneous, if possible? And the answer is we could. We could use this equation here or this formula and actually solve for when this reaction would become spontaneous. We know that it will become spontaneous when delta G is equal to a negative number, and that would occur on the other side of 0. So if we set delta G equal to 0 in this case, that would give us delta H minus T delta S. Putting in our numbers over here, T delta S is equal to delta H. Dividing this to the other side gives us a temperature that's equal to our delta H divided by our delta S. So if we put our values in for this, our delta H again, 177.8, I'm times it by 1,000 again to get it to joules, divided by my S, which is in joules, which is why we do have to do that conversion. R, again, convert it to kilojoules. That's going to give us 177.8 times 1,000 divided by 160.5. That's going to roughly give us there 1,108 Kelvin, which if I subtract 273 from to get our temperature in degrees Celsius, gives us about an 835 degrees Celsius. That is the minimum temperature at which this reaction would become spontaneous. And if we look at a graph of what's going on in this reaction, we could see the pressure of CO2 is pretty much non-existent till we actually get to 835, which is right there on the graph. And you may say it does start to rise before that, and you are correct, but it doesn't achieve sort of standard pressure of 1 atmosphere until about 835 degrees Celsius in this particular case. Now, that is a fairly large temperature. And remember, as to what we were just talking about, if we just analyzed our table here, our equation, we had a positive delta H and a positive delta S. And what that means is the only way for this backside, which is technically negative overall, to be larger than the front side is at a really high temperature. And I would say 835 degrees does qualify as a really, really high temperature. And that will allow that back end of the formula to sort of overtake the front end and end up with a negative value for delta G. Any questions on that there? All right, so let's try this one. Is the products or reactants favored at equilibrium here if the delta H is minus 1204 and minus 216 for our delta S? Okay, so again here we have delta H and delta G, so we'll use our equation that again has both of those guys in it. Maybe put our temperature in the equation too would be good. So we do again need to convert our temperature into Kelvin, so we'll add a 273 to it, so 298. And we'll put in our numbers here, minus 1204 times 1,000, again to convert it to joules, minus our T, 298 Kelvin, and our minus 216.4 joules there for our S. That's going to get us minus 1204 times 1,000 minus a 298 times negative 216.4. It's going to get us a negative 11,39513 joules, or roughly minus 1140 kilojoules. In this case, products would be favored as this reaction should be spontaneous as it's negative, so it should be heading in this direction. Any questions on that one there? So one of the things we talked about last time was the idea of phase changes. And when we do have a phase change with a substance, again, the substance is at equilibrium. And because it's at equilibrium, our delta G again in that situation would equal 0. And we could actually solve for delta S in this case. And for example, if we look at this, which is liquid going to gas, that is vaporization occurring here, or evaporation. And we could calculate what is sometimes referred to as the delta S of vaporization. And the delta S of vaporization in this case would equal our delta H divided by our T. And a couple of things about this sort of formula here. This is the delta S of vaporization and also fusion as well. It does not have the negative sign, and people oftentimes get this one confused with the delta S of the surroundings we saw, which does have the negative sign. So you do want to make sure if you're doing the surroundings, you need that negative for the opposite relationship that happens with the delta H. If you're really doing some type of phase change and looking for the entropy of a phase change, there is no negative in this one. So again, that's a very common sort of error that sometimes people make. So what do we got going here? This is liquid to gas, as you may know. That is the delta H of vaporization that allows you to do that. The delta H of vaporization is the energy that's needed to convert, in this example, liquid water to basically steam at 100 degrees Celsius is where that occurs for water. That is the normal boiling point for something like water and where that occurs. This right here is the delta H of vaporization. This is the 100 degrees Celsius plus a 273, right? So the normal boiling point that's happening here. And if we do this, we get a delta S of vaporization for water going from the liquid state to the gas state of 109 joules. And in this case, we actually get a positive value for our delta S of vaporization. And that does make sense if you think about it. It is transitioning from liquid, which is a more ordered state, to basically gas, which is a lot of disorder, things flying around all over the place. That means the amount of entropy is increasing, the amount of disorder is increasing, and we would expect our delta S to be a positive number in this case. Now, if we were doing basically the opposite transition where we were going from basically steam and going to water through condensation, and we want to calculate something like the delta S of condensation, it would be pretty much for water the exact same calculation. The only difference is as we go through the process of condensation, that is an exothermic process. Energy has to be released in that case, as gas molecules are flying around with a lot of energy. As they release the energy, they slow down and kind of stick to each other and fall into like the liquid phase, if you want to think about it that way. So what is affected in terms of the calculation here? It is actually the delta H of vaporization values affected. The value is actually not affected. It's actually the sign. Because it's exothermic, that delta H of vaporization going in this direction will actually be a negative number. So our delta H of vaporization, or really condensation in this case, is going to be negative 40.79 because we are heading in the opposite direction. It will still be the same boiling point where that occurs, and that would get you your 373 Kelvin happening. And that's going to give you the exact same number, except that it will end up being a negative number, which does make sense for going in that direction, because again, we're going from gas molecules that are flying around to liquid molecules, which are much more ordered, a lot less disorder happening. And again, that's going to give us a delta S that's going to be negative. Any questions on that there? Could also do this for the delta S of fusion, which is a transition from solid to liquid or liquid back to solid. Again, for water, the delta H of fusion is roughly 6.02 kilojoules per mole, and that occurs at 0 degrees Celsius. Now, it's important to also remember that these numbers we're talking about here in this particular example is specific for water. So if you were using some other substance, those substances may have a different boiling point and freezing point or melting point temperature, and they also will have different delta H's of fusion and vaporization. So it is specific, again, for the substance that you're dealing with. Any questions on that there? So why don't you try one here? The enthalpy of vaporization for mercury is 58.5 kilojoules, and the normal boiling point is 630. Okay, so again here, enthalpy of vaporization. What is the enthalpy of vaporization? So that is the transition again from liquid to gas is our assumption. They gave us the delta H of vaporization in this case, which is 58.5 kilojoules per mole, which again is different than obviously we see for water, because in this case we're dealing with mercury. In addition, our boiling point temperature, which is basically where that occurs, is also different than we see for water, and they actually have it in Kelvin. So we could use our delta G equals delta H minus T delta S. Again, because this is an equilibrium process, our delta G will equal 0. That's going to give us a way to rearrange this, that the delta S and T will equal delta H. And in this case, we'll solve for delta S, which would be our vaporization, delta H divided by T. Once again, this is why it does not have a negative in this formula, because it is actually derived from this equation. Putting this in, we're going to go 58.5. I'm going to convert it to joules, because S is usually in joules, so times that by 1,000. Temperature was already in Kelvin, which is great, so no conversion there. So 58.5 times 1,000, or 10,000 if you hit the wrong button. I'll try that again there. Times 1,000 divided by 630. That's going to give us a 92.9 joules per Kelvin as our delta H, our delta S of vaporization. If you did it in kilojoules, you got like a 0.092 happening in that case. Again, if we were doing the reverse transition going from gas to liquid or condensation, really everything will be the same, except that in this case, that would be negative if we were going from gas to liquid, and that would then give us a 92.9 joules per Kelvin negative if we were going gas to liquid in the opposite direction. That would be the only difference. Any questions on that there? All right, I think good time to stop, I think, yeah.